Greetings, geologist. You're back. It's time for sedimentary rocks, weathering, and soils. 75% of everything that you see out on the ground is sedimentary rocks. A much smaller percent is actually what makes up the crust because the layers build up and go down into the mantle, get subducted, and also turn into metamorphic rocks, into igneous rocks. But at the surface, most of what we see, that 75%, is just that. It's sedimentary rocks. When you look at this outcrop of the Coquina sandstone at the north rim of the Grand Canyon, it has a distinctive look to it. And you can even see that it has layers here. That's indicative of sedimentary rocks. They are layered rocks. So we're going to learn all about them today. So how are sedimentary rocks made? They're made by weathering and/or erosional processes. Two very different things. Oftentimes you will hear people use them in tandem, those terms. I want to be careful that we define them appropriately so you'll know how to use them. So weathering refers to the breakdown of rock material by wind, water, ice, gravity. So in this particular case over here, we have some weathering and some erosion going on where water and gravity has been creating a gully and it's eroding out. So when materials are actually moved out of an area, that's erosion. When they break down, that's weathering. So one year on field course, we had an excellent view of what's called frost wedging in Bryce Canyon National Park. Matter of fact, it's almost a whiteout here. It's not a fuzzy picture at all. It's actually what we saw in real person. And we'll be talking more about how hoodoos form later in the semester, but this is in Bryce Canyon, and this is a look at how that water is getting into the joints and fractures of that rock. And as ice forms, it will literally expand and bust it open. So any kind of weathering is going to do just that. It's going to break down pre-existing rock. Erosion's a bit different. Erosion takes those broken down weathered sediments and transports them elsewhere. So I'm going to point out the Colorado River. This is at Navajo Bridge. That's in Arizona, close to where you would go towards the turnoff of the north rim of the Grand Canyon. And the Colorado, you can actually see sediments that have been deposited right in here. These things are being weathered and moved downstream. So the movement part of it, that is erosion. When you look at the Grand Canyon, here's the gorge right here where the oldest rocks are, way down in this gorge section here. All of this is being weathered down and eroded. So eroded is the movement by the Colorado River. So you can have weathering and the absence of erosion, where let's just say you have a rock slide and a bunch of rock material just slides off the canyon base and makes a pile of rocks at the bottom of the canyon. That is not erosion. That's simply weathering. Erosion would be if some kind of agent picked it up, like water, wind, that kind of thing, ice, and transported it to a new location. So one of the most common culprits of erosion is actually water, and it makes sense why when you think about the surface water in rivers across the world. So a very important concept today you need to get clear in your mind is something called differential weathering capacity. So if you've not read your chapter 7, I'm going to ask that you stop this video and you take some time to read it, because we spend a lot of time going through differential weathering capacity, weathering erosion, all the various different sedimentary information you need to know, and then soils, and of course you will get at the end a review of all of those items. So I need to make sure that you have done that step, important to me, so you are fresh, knowledgeable, and ready to hear and absorb all that has to be shared about this topic. So differential weathering capacity refers to how fast or slow a rock weathers. So this is in Arches National Park in Utah, and I want to point out that this is the Entrada sandstone, here. Matter of fact, all of this is. And at one point they were touching, so the law of lateral continuity that we learned about in geologic principles applies. But the point is the entrada sandstone has not weathered at the same speed. Why is it that this section right here, all of this air, this section of the entrada isn't touching anymore? How did that happen? It has to do with something called differential weathering capacity. There is a low differential weathering capacity and a high differential weathering capacity. Within a same rock layer, even these right here, this is the Grinnell Formation in Glacier National Park on the Montana side, they can have different differential weathering capacities. Even within the same linear foot, you can have different weathering capacity, differential weathering capacity. How's that possible? Has to do with cementation, compaction, the degree of lithification, which is hardening. So let me get to the two types of differential weathering, and then we'll apply that to make sure you're clear on how it works. Low differential weathering capacity means a rock weathers at a slow rate. That's because it's more durable. So when you have low differential weathering capacity, a rock is very sturdy, durable. It will not erode in weather fast. So I use those terms together, but I'm going to show you in a minute exactly weathering and erosion together in this very location. So low, remember low rhymes with slow. People want to make it reversed, and it's easy to see why, but I need you to make sure you get those terms right. High differential weathering capacity. High doesn't mean it's strong, it means that it's weak. It means that it has and is prone to weathering fast. So let me point out in this particular rock, you see these slopes here? They're kind of angled like this. That's because they have a high differential weathering capacity. They are not very sturdy, so they weather quickly. Right above it, you see a canyon or cliff face. That would have a low differential weathering capacity. So when you're looking at places like the Grand Canyon, or in this case, Canyonlands National Park in Utah, you can see differential weathering at play by the landscape. So when it's vertical up and down, it's going to have a very low differential weathering capacity. When it's more slope like this, you're going to have a high differential weathering capacity. So I'm going to show you a geology moment over differential weathering capacity, and it was taken in Glacier National Park. Hope you enjoy it. It's a great place to visit. If you get a chance to go to this national park, you need to make a road trip and go see it.
Okay, you may be wondering how it's possible to have these cascading waterfalls, and it has to do with differential weathering capacity. This is all the same rock. To be clear, it's a pretty hard rock. It used to be like sandstones and siltstones, but it's been slightly metamorphosed, so it's a little harder. It's Precambrian in age, it's Proterozoic. It's one of the main rock formations in the park at Glacier National Park. I just want to address looking at these rocks right inside the riverbed there. You can see how fast the flow's moving, and it's not moving them at the moment. So this thing will gush worse during snowmelt conditions, which would mean it would flood more than what you see happening right here. So differential weathering capacity has to do with how fast or slow a rock weathers. So granite has a very low differential weathering capacity, meaning it doesn't weather very fast, but something like shale has a high differential weathering capacity. Apparently these rocks are pretty durable, so they have a low differential weathering capacity for the most part, but they have a major challenge, and here it is right here. Flowing water itself is not the worst enemy of rocks. Actually, plants are. Sorry about that, botanist. But it's what it can move that is the most dangerous thing in these streams, because that's what scours this stuff. So my guess would be that the different grades here are related to flash flooding events, because this is all the same rock formation. Down about a mile down the way is a giant waterfall, and that's going to have some pretty durable rock right there. Remember, it's the same formation, it's just not behaving in the same way in terms of how it's weathering. So more to come from Glacier National Park. See you at the next stop.
As we look at these various images of places, I would like you to kind of think which section of the arrow is low, which one is high differential weathering capacity. So we'll start on A here. First of all, you're looking at a man-made river, believe it or not, in Tropic Ditch, Utah, which is by Bryce Canyon National Park. Really pretty national protected public lands here that you can go see this gorgeous place. A is that slope area, so would that be low or high? Remember, low is slow, high is fast. So the slopes, they're not very sturdy, so that would be high differential weathering capacity. These sections right here should be connected, but they're not. And that means these rocks are a little bit more sturdy, so they have a low or slow differential weathering capacity. This is La Ventana Arch in New Mexico, all the same sandstone unit. So this is a very important place. This is the Zuni sandstone, by the way. And you can see this stuff hasn't weathered out to make an arch, but this has. So something's different here. Which one has the higher differential weathering capacity, meaning it's weathered more quickly and has prone to be so? Would it be A or would it be B? If you answered B, as in Bravo, you are correct. A has a lower differential weathering capacity. Remember, low is slow, high is fast. So this is in the Grand Canyon. These are the slopes of the walls of the Grand Canyon. So it's these slopes right here, really. It's the same rock material. And then you get the Coconino sandstone right here. So you got that canyon wall going straight up and down, vertical stop. That means it's very durable. So would that have a low or high differential weathering capacity? So B would have a low differential weathering capacity. A, which makes up the slopes, would have a high or higher differential weathering capacity as compared to this section right here. Once that you've learned differential weathering capacity, then we can get into some important terms: compaction, cementation, and lithification. This is Zion National Park, my personal favorite of all the national parks I've been to in the United States, which is most of them. And I can tell you that this place underwent a considerable amount of compaction, cementation, and lithification, but at different rates throughout the park. So I'm going to talk about both compaction and cementation here because this picture illustrates it well. This is all the Navajo sandstone, which is an early Jurassic deposit that was much more impressive than the Sahara Desert back when they were sand dunes. So you have to imagine these were ancient sand dunes. So why is part of it red and part of it is white? That has to do with compaction and cementation. So compaction would be like what you probably do to your trash, you stomp on it to make the air less prominent and allow for more space for trash. Well, in terms of rocks, that's going to happen when new rock layers get built one on top of the other and they push them down and they squeeze out the airspace between the different particles and rock layers. Cementation is the actual gluing material, the natural mineral growth that allows materials like little clasts to glue together and stick together. Well, in the case of Zion in the Navajo, this white material here in the sandstone has a less compaction because it has more grain space or pore space. So it is allowing the water to penetrate through it better, which is washing out the iron as opposed to the areas that are more red. They're compacted more tightly together, so the pore space is smaller and the travel space for water to go through. When we get to groundwater later in the semester, you'll learn this about porosity and permeability. What is cementation? It's a hard concept to understand, even though we can all relate to glue. Seeing it in rock pieces is different because it's just not normal, right? So I zoomed in on a piece of conglomerate here, and some of the materials on the outsides are just evaporite deposits, but you can see how these things are literally, these little clasts are glued together. This is a rock solid piece of rock, pun intended, right? But nevertheless, it's not loose. There's not a bunch of pebbles falling off. It is glued together. And I didn't do that. It was in nature that way. So that's cementation. That's the process of mineral growth between individual grains within a rock that allows it to be put together and glued together. So the rate of cementation, if it's fairly low, your rock's going to be fragile, fall apart. So in that case, it would have a high differential weathering capacity. What more cemented these rocks are, the harder it is to break them apart, to weather them apart, and so it'd have a lower differential weathering capacity. What does lithification mean? The term lithification or lithify means that you have a rock that has become hard. So the process of hardening a rock is lithification. So this is the Navajo sandstone again, but this one's near Page, Arizona, and it is on Navajo tribal lands. This is the Lower Antelope Canyon, one of the entrances to the Antelope Canyon, very famous slot canyon. So you can see that this rock has been hardened, but it used to be sand dunes back in the early Jurassic period, and now it is a rock solid material. So that's the lithification part. Sometimes I get students asking me, how slow or fast does it take to lithify rock? Well, that's a loaded question. It depends a lot on the depositional environment, how humid, if there are minerals involved, the rate of deposition in the area. So I'll give you a true story from Hawaii. So I was taking a class, I think I mentioned this in one of my other videos. I took several classes in Hawaii under a guy. His name is Chuck, and Chuck had us dig out a beach. And I can remember digging out this beach, and we were doing a profile to understand how beach sedimentation works. So we were digging down about 6 feet under, and as we were digging down no more than a foot, we came across a glass bottle that was a beer bottle dated the year before we were digging. And it was clearly embedded, so someone hadn't dug a hole and stuck it in there. It was buried in sediment. So just over the course of a year and about a foot of sand deposition, this got deposited and was part of the rock record. Kind of a weird deal, right? Well, that same situation, if you get a different set of sediments, a different location, might take literally 1,000, 10,000, a million years to bury, or it could be buried overnight in a conglomeratic flooding situation. So the rate of lithification and speed is dependent on all of those factors. So there are two major groups of sedimentary rocks. There's detrital/clastic, that means the same thing, and then there are chemical sedimentary rocks, and chemical are subdivided into chemical and biochemical. For this class, we'll just lump them into one called chemical. So we're going to start with detrital clastic sedimentary rocks. So I'm using the terms together because I want you to keep hearing them. They mean the same thing. First of all, what is a clast? Those are the individual fragments, like of the conglomerate you saw. Those are the individual pieces or grains of material. So clastic is a term that refers to rocks that are made up of other pieces of rock material, and it could have some organic material, whatnot, but nevertheless, it is broken up other pieces of rock. Detrital is the same thing. It's kind of like intrusive in plutonic and extrusive in volcanic for igneous rocks. Detrital and clastic are synonymous. So most detrital sedimentary rocks are they're called whatever they are, whether they're sandstone, they're siltstone, they're shale, claystone, mudstone. By the way, shale, claystone, mudstone, they're all the same thing. Has to do with the size of their grains. So the diameter width of their clast, the dominant average of that dictates how big the material is, and that in turn determines which rock classification or name that they are given. So here's that tropic ditch again in Utah, and you see how fragile this material is. And man, if you were to step on this stuff, I bet you would just go falling down. Not only is it steep, but it's so prone to weathering, has a very high differential weathering capacity. Rock material is just falling into this stuff, and it's going to be creating new rock material. That brings me to the sediment size chart. The size of individual clast within any given detrital sedimentary rock determines if it is classified as clay, silt, sand, or gravels. So why do we care about them? I'm going to give you a story of a friend that I have, still a friend today, just one of those people that didn't follow instructions when they asked for advice. First of all, this person has more money than they know what to do with. And that's important because they are building a new house in an area in which I live. I don't live in that particular area, but this person was building in a rather upscale location, a very like $1 million home. And they wanted to landscape their yard with river cobbles. They had gone to a restaurant that the two of us visited regularly together and saw this landscaping with big round cobbles from rivers and liked the xeriscaping and said, hey, I'll be a little bit environmentally friendly, and oh, I think I really like the round rocks and I want to do my yard in that, and I'll pay whatever it costs to get it done. And so I put this individual in touch with a lawn care company and a architectural design group that does xeriscaping, and said, when you order the rocks, you need to be very specific about what you're ordering, or else you're going to get a truckload full of junk, like lots of stuff that you're not going to use. Oh, okay. So I told her to order this right here, cobbles. And I said, specifically, you're going to ask for round river cobbles. Well, if you look at the sediment size chart, they're 64 millimeters to 256 millimeters in diameter. So you're looking at rocks that are fairly large. So you'd be looking at rocks like this. Big stuff, right? But specifically, she wanted it round. That's an important part of the story. Well, she calls and gets the person on the line for ordering the rocks, and they give the big old sale pitch. Well, we have a special, and you can get a truckload of gravels for XYZ price. And it was much cheaper than what they quoted for the round river cobbles. Well, let's look at what constitutes gravels on the sediment size chart. Pebbles, all the way down to 2 millimeters to 64 millimeters in size, the cobbles, the 64 to 256 millimeters in diameter, and then boulders, everything bigger than 256 millimeters. And in most cases, the boulders would be like this size right here, just giant, right? So basically, she got a truckload of junk. She got a truckload of some stuff she could use and just a handful of river cobbles. Of that, most of them were not pretty round ones like she wanted. They were subangular in shape. My point is this: it matters what you're using when you're building, like a road or a driveway. Let's say you decide to do a pea gravel or just a concrete driveway. Well, there's different prices based on the materials that they're using to make that. So the more consistent the size, the more expensive the material is going to be. And that's exactly what my friend didn't get. So she called the company and said, hey, I want my money back. I ordered these rocks and I wanted this. I wanted round river cobbles. And they said, well, you ordered the special, which was a truckload of gravels. So she had to pay to get them picked up and pay again to get the river cobbles and the xeriscaping installed in her property. Now, it looks wonderful, but she could have saved half of the money simply by listening to the directions. So let's get to the other three sections of the sediment size chart, which are very important for sedimentary rocks. Let's start underneath gravels is sandstone. Sandstone is made of sand. And you're like, well, duh. Well, let's do the duh moment and look at it a little bit more closely. It has a diameter range of 0.0625 up to 2 millimeters in diameter. That's a broad range. So just to call something sand because it feels sandy, you're probably right, but it must have a classed average size of anywhere from 0.0625 up to 2 millimeters. So if you're guessing that these would be excellent test questions, you bet, because the sediment size chart is used worldwide. It is a consistent sizing chart. It's important in multiple industries, not just geology. Siltstone has some sand material in it, but it's fine enough to also have some clay material in it. So it's going to be a transitional type of sediment between sandstone and shale. So it has a class size going from 0.0625 down to 0.002 millimeters, which is so small you need to start needing a microscope to see it. So you're like, well, that kind of borders with sandstone and shale, and it does on either side. So you've got to know rocks, be with rocks, touch a lot of rocks, see a lot of rocks before you get really good at differentiating the difference between siltstone and shale, siltstone and sandstone. So let's get to the smallest type of detrital sedimentary rock, which is shale. Some people call it mudstone or claystone. Bottom line, it's shale. And shale is made of clay. Clay has 0.002 millimeters in diameter and smaller. Bottom line is, if you took a millimeter reading of this stuff and looked under a microscope, there'd be too many of the little clasts to count. And with that in mind, if they're so tiny, it takes a long time to settle out, let's say, a foot of clay as opposed to a foot of pebbles, cobbles, and boulders, which are gravel. You could do that in one night with gravels. In one storm, big rise of water in the river, and it's carrying all kinds of stuff and dumps it all out, all size grains at once. Might take longer, and it will take longer to make a foot of sandstone, but a lot less time than it would a foot of shale. So when the smaller the grain the grain size of material, the longer it takes to settle out and make thicker strata layers. So there are different types of detrital sedimentary rocks, and some of this will be a review because you've heard about these already, even when we've talked in different sections. Conglomerates versus breccia. So conglomerates have predominantly rounded clast, like this right here. I'm not saying they're not going to have an angular clast somewhere, but about 50% or more, a majority of their clast will be rounded. The rounded comes from being bounced around at the bottom of a riverbed, and they usually travel a long way from the source material where it was weathered off before it got picked up in the erosional process. So on the right side, you see breccia. Well, breccia has very angular clasts. So essentially, the story would be, okay, we had some kind of mass wasting event, like a rock slide or some kind of a rock fall, and a bunch of stuff fell and got buried very quickly. It didn't travel very far from its source like our conglomerates did. It's a clue, it's a story. So each one of these rocks has a special, unique story that they indicate simply by the morphology, the shape of their clast size, and their size of clast. So in both cases, these rocks will have all different grain sizes from real tiny to very large, but they usually have clast sizes that are 2 millimeters and larger, and that's clearly the case in both of these illustrations here. Sandstone. There are 3 different types of sandstones, just so you know. And sandstone, there's one, we'll kind of limit it in this class to having arkose sandstone or quartz sandstone. Quartz is going to be on the higher diameter size range, anywhere from probably about 0.5 millimeter up to 2 millimeters in diameter. And then your arkose is going to be a finer grained sandstone because it's made of more of feldspars, which makes clay, and it's going to be closer to the 0.0625 millimeters. The point is that they're sand-sized grains, and that's what makes sandstone. This is a ideal quartz sandstone right here, and if you touched it, it would feel very rough and sandy to you. But the real way you determine if you got sandstone is you put it under a hand lens or a microscope and look at the sand grains. And like if it's quartz sand, most of the time it'll be pretty rounded unless you've got a something called dirty sandstone. But in this case, we're going to just talk about arkose and quartz sandstone. So let's move on to siltstone. Like, well, it kind of looks like sandstone. If you could touch this, it's not as sandy, but it does have a gritty feel. And it's not very smooth. So siltstone is the stuff that is in between sandstone and clay-sized stuff. It's from 0.0625 millimeters down to 0.002 millimeters in diameter. You would probably recognize this as the material that gets caught in silt fences at construction sites, because the silt fence is designed to catch small grain materials like silt that washes off during storm events. So in comparison to sandstone, siltstone is going to have a much lower energy of water movement as opposed to sandstone. So I'd like you to think about a beach for a minute. And beach waves would generate a considerable amount of energy. If you haven't seen a beach, Google it and do beach waves and just see what that looks like, the amount of rigor and vigor and energy that's moving around in that water, so it can carry larger grain sizes. The slower that water gets, the smaller the grain is going to be, and that's certainly the case for siltstone. Then there is shale, which is clay. So remember, clay-sized stuff is shale. That's stuff that is typically less than 0.002 millimeters in diameter. It is in very low energy environments. You can make shale in lagoons. You can make shale in the bottom of lacustrine or lake environments. You can make even shale in a fluvial or river system if you get an intermittent stream like a pool. And you'll be learning more about that later in the semester. But you can form shale anywhere where there's low energy water conditions. So there's a second type of sedimentary rock called chemical sedimentary rocks. These are not predominantly made by broken up pieces of other rocks and minerals and biological stuff. There can be some of that in there, but it's primarily made of a chemical process. Like it's going to have 50% or more of it made by this chemical process, which could include precipitates, which is a solid that falls out in solution, or in many cases, dead organisms. And those dead organisms are not always big fossils. Most of the time, they're microscopic, like the picture you see here of foraminifera on the right. So I'm going to give you a story about them in a minute. So let's talk about ways that we can make precipitates happen and make the actual solid material that constitutes a majority of the volume of a chemical sedimentary rock, because it's not going to be a majority made up of broken up other rocks. That's detrital clastic rocks. This is in Mammoth Hot Springs in Yellowstone National Park, and this particular place is a travertine outcrop, which used to be limestone. Well, limestone is a chemical sedimentary rock. So what happens is, to make that limestone, you're going to have literally, depending on the type of limestone, you'll have millions, if not more than millions, of little bitty microscopic animals that sink down into layers of mud, carbonate mud to be exact, which is going to be limestone stuff, and then it gets compacted and cemented, and then it gets lithified, which means hardened, and it turns into something like limestone. So you can have chemical sedimentary rocks that have macrofossils instead of microfossils, but so much of it is these chemical rocks are made by little bitty microscopic stuff. So I'll take a moment to respect them and talk about something like forams and diatoms and radiolarians. Some of these little dudes actually have a small amount of like an oil product in them when they're alive, and it's used for their photosynthesis or their feeding mechanism. And when they die in mass numbers, like a mass extinction or a climate change event, they will sink to the bottom, and then they get pressed by new stuff on top, and it oozes and smushes out that oil product, and that's how we can make hydrocarbons, fossil fuels. So I know that you probably heard somewhere along the way that most of our fossil fuels comes from dead dinosaurs. I'm not going to say that none of them do, because we do have some that have. But when you go fill your car up next time, I want you to think about little guys like this and respect them, because they have provided us with a rich array of fossil fuels around the world. Another process for making sedimentary rocks is a process of evaporites. So let's say we get water that has halite in it, salt deposits, right? And it evaporates off of land. It's going to leave a solid behind, which is a salt deposit. These are salt flats in Badwater Basin of Death Valley National Park in California. So these dissolved minerals that are in water become solids when the water goes away, when it evaporates. So evaporites kind of are important for a clue, because if you have a bunch of them like the salt flats here, that tells you that you had saline water there at some point. So that's another clue. When you think of precipitates, another thing that can happen is that we get a solid that falls out of suspension when it's in an aqueous type of situation. So on the left you see a test of making calcium carbonate, which is going to be calcite. And the calcium carbonate, you can see solids are starting to fall out of suspension here. And that is what's going to make up this. And I will also tell you they're microscopic dead organisms in this. So this is at Lover's Leap in Waco, Texas. It is a big outcrop of the Austin chalk limestone, which is Cretaceous in age. And it's made up of precipitates and microscopic dead animals. There are various different types of chemical sedimentary rocks. We're going to start with the limestones and work our way into the others, just like we did with detrital. So just a quick review for detrital, you had conglomerates and breccias, which were the largest class size, and you had sandstones, and then you had siltstones and shales. So we've moved now from detrital/clastic into chemical and biochemical sedimentary rocks. Biochemical limestone is by far the most common type of limestone that you'll find, and it's made up of skeletons of dead marine organisms. So those skeletons, like this is a classic biochemical limestone, and it's based, and I found it in Brownwood, Texas. So it's kind of Paleozoic in age. That'll matter if you take historical. So they're somewhere between like 542 million years old, or really closer to about 250-ish million years old. But nevertheless, they're made up of invertebrates, of animals that lived in a marine environment. Chalk limestone is also made up of dead organisms, but they're going to be microscopic in size. Chalk has a chalky feel to it. It's also softer than most of your other types of limestone because it contains a clay product called marl in most cases. That's certainly the point of this one right here. This is from Lover's Leap in Waco, Texas. Very much a chalky type of limestone. So chalk limestone does just that. I mean, that's kind of where we get our chalk, is from that material, calcium carbonate. Now, my personal favorite limestone is Coquina Limestone, which is this stuff right here. So what is Coquina? Basically, it's loosely cemented. So remember, cementation is the glue, right, that keeps the stuff together. So yeah, this has some detrital stuff in it, but it's still limestone. It's still made of at least 50% of chemical stuff that makes up limestone, calcite to be exact. So while these shells are loosely cemented, they are made of calcitic material. You can see the shells without a microscope. You look at this, this is like the best coquina I've ever seen, a whole outcrop of it in Australia. And so I brought this home with me because I wanted to show people what a really good coquina looks like. It's very fragile. If you thump this, some of the stuff will break apart because it's not very well cemented. Oolitic limestone. That sounds ominous, doesn't it? Oolitic. Well, this type of limestone has these little grains of material, spherical grains, and typically it could be little sand grains that get coated with calcite, and they make kind of balls. And those balls constitute the majority of the or a majority of the limestone, and they're cemented together with calcite. So oolitic limestone, very common, and it gets made in caverns and warm, shallow seas, so you'll see a lot of this out in nature. Well, there's another type of chemical sedimentary rock that's closely related to limestone but slightly different, and that is Dolostone. What makes it different is it has one molecule of magnesium while limestone does not. Not a big deal, right? Well, it is, because it makes it harder. The magnesium actually allows for Dolostone to not weather as fast, and so it is a different rock than limestone. So the mineral that makes up dolostone is called dolomite, which is different from calcite. So most dolostone will not react to acid, but unless you smush it up into a powder form, and even then, depending on how much calcite is there, it may or may not react. So that's one way you can kind of tell the difference between dolostone and limestone. They look a lot alike. So on to Chert and Flint. Some of people's favorite chemical sedimentary rocks because they make up arrowheads, points, spears, that kind of thing. So Chert and Flint, what are they? There are actually microcrystalline versions of quartz. Well, they've gone through a second precipitation process. Most of it is derived from limestone, which is reprecipitated in another aqueous environment. So it's made up of siliceous, which is silicate-based, like quartz-based skeletons of marine plankton. So they're harder than most of the calcitic material that's in limestone. They get dissolved during diagenesis, and that happens when the material is being made, the actual material of the chert and flint. So chert and flint represent reprecipitated versions of chemical sedimentary rocks, and they've been altered so they're much harder and durable. So this stuff, if you have chert and flint, there is a fundamental difference between the two, and it's the microscopic organisms that make it up. Flint tends to be more characteristic of marl-based materials that are carbonate. So just as an FYI, color is not the determining factor. It is actually what makes up the dead animal that actually is accumulating and reprecipitates in to make the difference between chert and flint. For all practical purposes, I am totally fine with you interchangeably using chert and flint as the same meaning. Moving on to sedimentary structures, you can follow right along in our book and you'll see where we are. We're going to talk about stratification. So we've mentioned strata before, that these refer to rock layers. Well, when you talk about stratified rock layers, layered one on top of the other, there's a difference in whether they have laminations or they have beds. So laminations are very, very fine, thin layers, and so they're going to be less than 1 centimeter in thickness. This is a piece of shale showing you some laminations within the shale, very, very tiny. They're a fraction of a centimeter. These are rock beds, so they're greater than 1 centimeter in thickness. Now, I'm not saying that you wouldn't have some laminates in here. You likely would. But when you're out in the field and you see laminations versus beds, that is another clue, because it's telling you about the type of rock that could have made those layers. The thinner the rock, the thinner the layers, so you'd have more laminations and things like shale, and you'd have more beds and rock material like sandstone. We've already learned about graded beds and depositional environments, so this should be a review. Remember, the big stuff falls out when the velocity of the water slows down, and then the medium-sized stuff, the small stuff, and then the tiny stuff. And that's because it's carried in suspension at a high velocity of water flow, and when that water flow stops, it all falls out in sequence. Here's that graded bed in the petrified forest there, showing you that even boulder-sized material can be picked up. So when the big stuff fell out first, medium stuff, small stuff, and tiny stuff. We've also learned about crossbeds in depositional environments. So remember, the high-angle crossbeds represent Aeolian depositional environments, while very low angle beds, like certainly less than 10 degrees, would be associated with fluvial crossbeds. So I'm going to give you a quick look into crossbedding in Zion, another geology moment, and hope you enjoy it.
Welcome to Zion National Park. This is truly one of the most beautiful national parks and the best kept secret of the national park system. What you're seeing behind me are massive sandstone outcrops of Navajo sandstone, which is early Jurassic in age. So what does that mean? It means that it's over 200 million years old, or between 200 and 150 million years old. It means that this was a time back when this area of Utah, matter of fact, most of the Colorado Plateau was a vast desert, just like the Sahara. So what these are lithified, that means hardened sand dunes. And they're stacked one on top of the other. They're as tall as over 2,000 feet. And they are just monster huge. Couple of important features about the sandstone. It's very porous. So that's why you see different colors, is because the sandstone, actually the water drains through it in some parts better than it does through others. So if it drains well, it will wash out the color. If it doesn't drain very well, it will oxidize and make a very red color. So it's still the same rock in most cases. There's a few different rock formations in the park towards the bottom that are softer, and that plays a role in how wide the Virgin River Basin really is. So this is all sandstone stuff, and it's heavily cross-bedded. What does that mean? Cross-bedding refers to the fact that wind blows sand dunes, and when it does, it blows it up the windward side and then it topples down the other. So you get a crisscross pattern that gets locked in the sand dune. Well, these are lithified crossbeds, and they're the best in the world, and I'll be showing you some as we approach the east side of the park. So stay tuned for more. I'm going to step away so you can see the view for a few minutes.
So here's excellent cross bedding that you can see in Zion National Park on the east side of the park. I hope you get there to see it in person. We also talked about ripple marks. Last time I gave you a overview from Glacier about ripple marks and mud cracks. And remember, they represent where water or wind has left ripples on substrate, and that substrate got buried. Just telling us a lot about that it's a transitional type environment like a tidal flat. So when you see ripple marks, there are two different types, asymmetrical and symmetrical. So asymmetrical means that the water moved in one direction, or the wind. So just moved this way instead of oscillating back and forth. So if you get oscillating types of ripple marks, that is symmetrical. That means you had it going in two directions, so it didn't just wash one way, it washed the other way. Mud cracks. Mud cracks are going to form, just like we talked about last time, wherever you have dry enough areas where you get rain and it saturates the soil and then it evaporates pretty quickly. And sometimes these can get buried by new sediments right on top and then cemented, and this is what they look like when they're lithified. Biogenic structures. We learned about trace fossils last time as well. So trace fossils are the evidence that animals once existed, or plants or microorganisms, any kind of fossil. And bio, meaning biological, biogenic structures are just that, they're fossils, specifically trace fossils. So that moves us into weathering processes. You might want to take a break for a little bit, and then we will come back. So just hit pause and we'll come back and do weathering processes after you've had a chance to get a beverage and some popcorn, whatever you need to settle down to learn about weathering processes and then soil formation. See you back in a minute. Alrighty, you ready? I am. I'm ready to get through weathering processes. All right. Really cool stuff. Physical and mechanical weathering. So there are two types of basic weathering. There's physical and mechanical, kind of like detrital and plastic means the same thing. And then we have chemical and even biological types of weathering. So let's start with physical weathering. You're looking at a tree that's growing out of the side of Glacier National Park, a cliff. You might wonder why it has a curved trunk. If you hang in a little longer in this semester, you can find out why. That's kind of an important thing. But what happens in physical and mechanical weathering is some kind of process, and this involved the tree, so it could also be biological. But the presence of this root and the tree trunk actually mechanically split apart rocks. So I think about physical and mechanical weathering as the tool that you would use to break up pecans. and that you might make a pie for the holidays. So if you've ever done that and painstakingly had to crack open and you've used that nut cracker, then you know that it's a lot of work. So that's kind of what rocks do. So frost wedging is a very common way that we make physical and mechanical weathering. So I showed you this earlier from Bryce Canyon National Park, and this is what it looks like when it's not snowing. But as the water gets in between the joints and fractures of all of these hoodoos and rock formations, it expands. The ice can expand up to 9%, and that's going to cause expansion in the rocks and literally mechanically break it open. So frost wedging can create really special features, not just some mass wasting of rock layers, but some features like hoodoos, which you'll learn about at the end of this semester. Another interesting physical weathering is exfoliation domes. Well, you learned about that when we showed you Yosemite and igneous section. I showed you the exfoliation domes and how they were busting apart the granite. Well, that's what you're seeing here. This is an Enchanted Rock State Park, which is located near Llano, Texas. And this is a big batholith, or part of one, and you can see where it's got fractures and joints on it, and where big slabs of granite are falling down. These are some of my students, and they're studying these rocks. And so exfoliation domes deal with primarily granite, and the granite's been uplifted and or the layers above it weathered down, and when that weight comes off of it, it causes it to crack at the surface, and then it can start weathering apart. Thermal expansion. Depending on where you live, if you have a drastic change from day, like nighttime and daytime back to nighttime, it could be as much as a 30-degree change for rocks, literally, in the temperature of the rocks themselves, and this can put a lot of thermal pressure on the rocks. So that can cause them to buckle and break. And so that's what thermal expansion is. Where I live, this happens in roads materials, especially during the summer. If you live maybe in an area that is up north somewhere, the ice can do this. So it can be another form of thermal expansion. But rocks are not really good conductors of heat. And so what will happen is this drastic change during the day can kind of put the rocks into shock a bit, and they just cannot handle the shrinking and swelling that they go through, and so they buckle, and this is exactly what happens to them. All right, so another type of physical weathering is called salt growth, and you get salt crystals that grow and actually cause hollowing out of rock material. A similar type of thing can happen in a chemical weathering process. This is called honeycomb weathering. I took this shot in Capitol Reef National Park in Utah. And so salt is the main culprit for this happening. So if you see honeycomb weathering like this, you'll know that there was a type of weathering that occurred to cause that. All right, so let me kind of compare physical/mechanical weathering to chemical and biochemical weathering. So biochemical, or biological, really I should call it biological weathering, involves some kind of plants or trees. So that's a self-obvious one. The chemical is not so much so, but I need to be frank about any kind of weathering. Rocks are going to be weathered from the outside in, not from the inside out. So I'd like to think of it as once you get a rock broken, layer by layer, then you can start getting to the point where you can make it into much smaller pieces and ultimately dissolve it away. So if you had physical weathering happen to a rock and then the opportunity for chemical weathering to occur, it will weather faster. A very common form of chemical weathering is oxidation. So if you travel out to the southwest in the United States, so many of the rocks are very red, and that comes from any type of metallic element that could be in that rock that reacts with oxygen, and it basically rusts it. So here is oxidation, and actually a special type of chemical weathering called desert varnish, which is manganese oxide that can actually discolor and form a chemical reaction on rocks. So you can see there's been an arch missing right here, and it's fallen down, so there's been a rock slide. And some of that's probably due to physical, but the rest of it's chemical weathering, where you can see this background here where there was material that got in there and loosened the rock. So never underestimate the power of chemical weathering. Hydrolysis is a very common type of chemical weathering. This type of chemical weathering occurs when a mineral is altered to become another type of mineral in water. This is probably the most important way we make soil, especially from granites. As granite decomposes, the feldspars fall out and they make our clay-based soils. So this process of going from a rock that has feldspars, like igneous granite, and then it decomposes into this, is super important for formation of soils. Solution is another type of chemical weathering, and this is very similar to what we saw with the honeycomb weathering, but what happens is the water is slightly acidic. So you get rainwater that comes through the atmosphere and it picks up a little carbon dioxide, and it can transition into something called carbonic acid, which is a weak acid, very similar to what I was squeezing on the mineral calcite when I was showing you that in the mineral lecture. So what will happen is that water will slowly eat away pockets on rock, and when it does, it will make cavities, and that's what solution is. It's actually eating away part of that material of a sedimentary, igneous, or metamorphic rock. It's just a form of chemical weathering. So backtrack for a second and appreciate that when weathering happens, it usually happens together. So you can have biological, physical, and chemical all in the same area. Sometimes you just might have one type occurring in a region. But most of the time, there's different types of weathering occurring. And weathering is going to be accelerated if there's a fracture or joint in a rock. So the more slices it has, the more openings it has, the faster the rate of weathering agents can work on that rock. So that is also an important factor when we're looking at differential weathering capacity that we learned about earlier. So let's move into soil formation. The earth is made of regolith. Fun word, isn't it? Regolith. So the surface contains regolith, which is our sediment, our weathered materials, even volcanic ashes and pyroclastic deposits. And regolith contains some plant material, water material, and rock material and soil, allowing for the growth of plants. So without regolith, we can't have biology, especially botany, going on out in nature. So in a perfect world, we would have a soil horizon that has 1, 2, 3, 4, 5 horizons with perfect transition zones between each of them. Reality check is most places do not have that, so we may have to manufacture something like an O horizon. So the O horizon is the darkest layer. It's the most organic. This would be places that you might find earthworms. You would find lots of bacteria working. It's the humus layer. It's going to be really organically enriched. Without a healthy O horizon, good luck on having any kind of plants grow in your yard, like if you want to have a garden or whatever. So most people have to manufacture that and buy fertilizer. Beneath the O horizon is the topsoil layer, known as the A horizon. Don't confuse topsoil with the O horizon. Two very different things. This also is biologically active, but not as much so as the O horizon. You can still have bacteria, earthworms, and so forth, but it is a necessary process of the transition from O to A. Then there's a layer in between A and B that is called the eluviation layer, and that allows for minerals to leach from O and A into the B layer, which is called the subsoil layer. So the E layer is the eluviation layer. It's an important layer. It's lighter in color, and again, that's where leaching occurs of minerals. So in the B horizon, the subsoil, you have a lot more, or should I say a lot less biological material and a lot more rocky material. And as you get into the C horizon, you're going to see all the broken up rocks, and they can start working their way and floating up to the surface. So I had a group do an undergraduate research study in one of my classes, and they did it over why do rocks grow in my yard. And this is exactly why they do. Because you get the bedrock becomes loose and they work their way up over time towards the surface. So your soil is a direct relationship to whatever bedrock's being weathered down. So rock gets weathered, turns into soil, soil can lithify and turn into rocks. All of it's related. Which brings me into soil that gets compromised. So when you have soils that begin to get weathered and eroded, problems can happen. So let's talk about rills and gullies, because if you get compromised soils, erosion can make your land less available for cultivation. It decreases its soil fertility, and also can become something that will no longer yield very good movement of water and groundwater and so forth. So rills are small little cuts in ground that are 30 centimeters or less in depth. So this is a rill right now where I'm living, and you can see it's not very deep. It's probably about 20 centimeters deep. This is a gully. So this is in Marble Junction in Utah, which is a junction you can either go to the Grand Canyon or to Zion. So both of them are great, but I'd turn and go to Zion if I was at that junction. But anyway, you can see how deep this is, but this started like that. So you can start with a little bitty crack, and over time that turns into a monster huge hole in the ground. Erosion's not a good thing. It's not good for the environment. It's not good for water quality. It is not good for land use. It's not good for humans. But it's a natural process of material. So we have to do some work to try to help and prevent our soil from degrading into something like this. And so best management practices known as BMPs can be utilized to help reduce the amount of rills and gullies, especially in agricultural arenas. So as we conclude, on the weathering side, I want to remind you that weathering happens in tandem typically with other types of weathering. This is Horseshoe Bend in Page, Arizona, a very famous place. So you got the Navajo sandstone, and you've got, that's a detrital sedimentary rock, by the way. You've got fluvial depositional environment down there, and it's an aeolian environment as well. It's desert. So you got river weathering, and if it's picking up sediments, that would be erosion. We're going to have some jointing, and then you'll have some chemical weathering that can get in those joints, and then you have, if you had any kind of mechanical weathering, that's all happening together. So even some biological weathering down in this section right here, even towards the top, there's some plants that are impacting the rocks. My point is that it's holistic. When you're thinking sedimentary rocks, weathering, and soils, they're interconnected. And when you see a landscape, I want you to now realize that probably more than one thing's going on to make it look that way. And especially when you're looking at sedimentary rocks, they just have so much to consider with the various different types of weathering. See you next time when we come back to learn about metamorphic rocks. Hope you enjoy the nature moment today, and I will see you back soon. Bye.